Okay, so in this section, we are going to start using the limits that we've been learning about, and we're going to use them to define the derivative of a function at a point. And if you remember back in section 2.1, we talked about secant and tangent lines, and we said that a tangent line touches the graph at a point and is sloped in the same direction. So if you can see this red line here, that is the tangent line. Okay, let me change that. And it is tangent at this point that's labeled a f of a, right? And so what you should see, okay, first before we say that, so the tangent line, as we defined it before, the tangent line at x equals a touches the graph at the point a, f of a, so that's the point on the graph right there, and is sloped in the same direction as the graph. Okay, so the issue with this, there's nothing wrong with this definition. It's just not very mathematically rigorous, right? And so what we want to do is actually use our limit notation and our limit language that we now have to define this mathematically. And so we can see that there are several secant lines drawn. They all pass through the point A, f of a, and they hit some other point on the graph as well. And so you can imagine starting from x1 here and drawing the secant line, and then moving to x2 and drawing the secant line. And so as we get closer and closer to A, you see that these secant lines, their slopes get closer and closer, and they start looking more and more like the tangent line, right? And so what happens, basically, what we want to do is say that the slope of the tangent line at A is equal to the limit as x goes to A of the slope of the secant line. The secant line through x and a, right? Okay, so this is not yet perfectly rigorous, right? But this is the idea. So we want to use a limit of the slopes of the secant lines. And the notation that we're going to use for this slope of the tangent line at A is f prime of A. So it is going to be f, a little apostrophe, before you write the parentheses, and then A. Okay, and then this you read f prime, so that little apostrophe you read as prime of A, right? And so this is the notation, and this is actually going to be the derivative. So whatever value we get out of this limit is going to be the derivative at A. So I'm going to actually write all of that down. So we're going to have two different definitions of the derivative, but they're really the same. So I will hopefully be able to convince you of that. So I'm just going to draw a picture of a function, looks something like this. And here will be the point in question, the point A, right? And then, so we want the slope of the tangent line, and we want to write that as the limit of the slope of the secant line through x and A. So if x is some point not equal to A, then here I'll use a different color for this. Then if we follow this up, we get this point on the graph and this point on the graph, and then we connect them, and that will give us our secant line, right? Okay, so the slope of that line, we can just use these 2 points that lie on it to compute the slope, right? So this point, if we evaluate it, so this graph is f, that means that this point over here, the height of it is going to be f of x, and over here, this will be f of a. So what we get is that this point, if we want to write it in coordinates, is x f of x, and then the coordinates for this point are a f of a, right? And so we're going to use those to compute the slope. And so what we get is that, so f prime of a, just so it's really clear what we're doing, I'm going to copy this down. So we want the slope of the tangent line at a, and we will find it by taking the limit as x goes to a of the slope of the secant line through x and a. Okay, so our notation for this is f prime of a, so we'll write that, and then this will be equal to the limit as x goes to a of the slope of this. So we just use these points and we write down the formula for the slope, so it'll be f of x minus f of a, so those are our y coordinates, and then x minus a, right? So that is one definition. So just, this is the first definition, and then also we're going to talk about the other definition. So I'm just going to draw basically the same picture where I have a point A. Maybe I'll make it, try to make it look more like, okay, so basically the same picture, and we have a point A, and we have a function f. And all I'm going to do is rewrite this point x as a plus h. So instead of thinking of x as just being a point in the domain that's not equal to a, I'm sort of thinking about standing at a and then moving a distance h away, and that will land me at a plus h, right? Okay, so then if we just draw the same picture, if we write down, so we'll have the secant line going through these 2 points like that, and then this will still be f of a, and this point will still be a f of a, right? But now that we're referring to this point as a plus h, it will just change our notation a little bit. So this will be f of a plus h, and this point, the coordinates will be a plus h, f of a plus h, right? Okay. Now, what we get then, if we write down our limit, so it's just going to be the limit as, so notice that, so it will help to do a little simplification before we write this down. I'm just going to draw in this triangle like this, and just like how you would compute rise over run when you find the slope of a line, that's what we're doing right here, right? So I'm just going to clean this picture up a bit. So the idea is you want this distance and you divide it by this distance. Now this is going to give us just f of a plus h minus f of a, right? And then this distance, it's just h, right? So we could take a plus h minus a, and that will give us just h for this distance here. So that means our slope is this quantity over h. A plus h minus f of a over h. And so we're taking the limit as h goes to 0. So as h goes to 0, this will get closer and closer to the actual point we care about, which is a. So this is our second definition. One thing I want to clarify is that the way that I've drawn all of these pictures, including this one up here, although I didn't draw it, it looks like we're only approaching from the right-hand side, but that's just because it's convenient for drawing the picture. Actually, you should be approaching from both sides. So you could also have an x over here and imagine approaching it from the other way, right? So because this is a two-sided limit, the limit as x goes to a, we have to approach from the left and the right. So just make sure that that's clear. Okay. And also, for this limit, it's the limit as h goes to 0. So h will be approaching 0 from the negative side, so small negative numbers, and then small positive numbers approaching 0. Okay, so hopefully you can see from this picture that these quantities are exactly the same thing. All we did was change our variables a little bit. So this gives us the same exact thing. These are the same, these definitions. Okay, so let's go ahead and do an example using the definition that we just wrote down. So you can use either one. So I'm going to use both of them in this first example so that you can see both ways. Okay, so we just want to set up our limit. So we want to find f prime of 3. So that means that our a here is equal to 3. So f prime of 3 equals, so I'm going to just write out the definition of the limit with the a still in there. So this would just be copying down the definition. And then since we're taking a equal to 3, we're going to plug that in everywhere there's an a in the definition. So it will be the limit as x goes to 3, f of x minus f of 3 over x minus 3. And that is the limit that we want to compute. Okay, so our formula for f is 1 over x. So for this first part, we just plug in, we just write down the formula, so it's just 1 over x. And for the second piece of the numerator, we plug in 3. So that'll be 1 over 3. And then the denominator will just stay the same. Okay? Okay, so this is a complex fraction, so how we usually deal with this is we try to simplify the complex fraction. So we multiply by the least common denominator of these two smaller fractions in the numerator. And actually, I'll give myself a little more room. What we get will be, so the x's will cancel and we'll get a 3, and then the 3's will cancel and we'll get an x. So we get 3 minus x over x minus 3, right? Which is just going to simplify to -1. There's something missing. Oh, the 3x. Okay, sorry. Oh, my eraser's not working. Okay, there we go. Okay, we have x minus 3 times 3x. So I have to multiply by the 3x in the denominator as well. And So if I cancel this with the factor of x minus 3 in the denominator, I'll get negative 1. So I would get negative 1 over 3x. And now if we plug in 3, we don't get 0 in the denominator, so we can just go ahead and do that. And this will give us negative 1/9, right? Okay, so that means that the derivative of this function f at 3 is equal to 1/9. And that means that the slope of the tangent line of that function is equal to negative 1/9. Okay. Now we can do the same thing just using the other formula for f prime, and we should get the same answer. So hopefully everything works out, and we do. So in this definition, I'm just going to copy it down. So this is directly how it was written, and then we plug in a equals 3 because that's the point we're interested in. So we'll get f of 3 plus h minus f of 3 over h. And next from here we want to evaluate f at 3 plus h. So that means that we plug in 3 plus h for our variable. So that would give us 1 over 3 plus h for that first part, and then f of 3, which is just 1 over 3, and then h. So we end up with a similar thing where we have to simplify by multiplying by the least common denominator of these two fractions in the numerator. Okay, so if we go ahead and do that, we'll get 3 minus 3 plus h, make sure to keep the parentheses on that, and then we get 3h, 3 plus h. Okay, and then those 3's will cancel, we'll get negative h in the numerator, 3h, 3 plus h. So these h's will cancel, and we will get the limit as h goes to 0 of negative 1 over 3 times 3 plus h. So we can just go ahead and plug in 0, and we don't get 0 in the denominator, and everything works out, and we get negative 1/9 again. So that's good. Okay, so our answer is negative 1/9. Okay, so let's do another example. This function is a little bit more complicated than the previous problem, so I'm only going to do it one way. So I'm going to go ahead and compute this. So one thing to know is that sometimes it's nice that we have these two different definitions because one is easier to compute than the other. So, you know, if you set up your limit and you don't really know what to do, you might want to check and see if the other definition would make the limit easier to compute. Okay. So g prime of 1, so that means that our a here is equal to 1, and I'm going to use the definition where we have h going to 0. And then so that means that we have g of 1 plus h minus g of 1 over h. So I went ahead and plugged in a equals 1 already. Okay, now what we get for the first part, g of 1 plus h, we have to plug in 1 plus h into our function here. So we will have 1 minus 2 times 1 plus h over 3 plus 1 plus h. So remember, you have to plug that in everywhere you see a variable. Okay, and then g of 1, that just means plug in 1, so here we would get 1 minus 2 over 3 plus 1. Okay, now this right here simplifies to negative 1 over 4, right? So I'm going to rewrite that as, so I'm going to get this whole thing over h, and I'll have plus 1/4. And then let me simplify this a little bit. So we have 1 minus 2 minus 2h over 4 plus h, right? And then this is a similar limit to the ones we were doing before, so we just multiply by 4 times 4 plus h, and we will get, so these 4 plus h's will cancel, and I will get 4 times this thing in the numerator, which I'm going to simplify a little bit, so that would be negative 1 if I combine 1 and negative 2, like that, and then we'll get just plus 4 plus h, and then this is over 4 times h times 4 plus h. Okay, now we just have to simplify a little bit, so we get negative 4 minus 8h plus 4 plus h, and that means that this negative 4 and positive 4 will cancel, and then we will get negative h plus h, so that's negative 7h in the numerator, and the denominator stays the same. And now we have an h in the numerator and an h in the denominator, so we can go ahead and cancel those, and then we'll be left with, it's already here, the limit as h goes to 0, negative 7 over 4 plus 4h. And now if we plug in 0, we don't get 0 in the denominator, and we'll just get negative 7 over 16. Okay, so that's going to be our answer, right? So one thing I do want to mention at this point is that I want you to be very careful with your limit notation. So when you're writing these things, don't drop the limit until the very end, when you're done simplifying and you're actually ready to plug in h equals 0. That's when you can drop the limit and just write it as a number, okay? But not before then, okay? And I do want to see like equal signs between each of these, and your work should go clearly in a line, not like maybe in a circle or something like that. So just make sure that everything stays nice and neat, and that will help me be able to read it. And also be careful where you put your equals signs. So there shouldn't be an equal sign right after a limit, like something like this equals. So that wouldn't be good because you don't have anything that you're taking the limit of. So this is almost like an incomplete sentence, like it's missing an important part, right? So this is bad notation. Okay, so we're going to do some more examples in the next video.